Hello, I'm making this video to show the process that I use or the workflow for astrophotography. A friend of mine asked me to put a video together to show how I do it, and that's what this is. So shout out to Chris O'Neill, who wanted to learn a little bit more about it. Okay, so I put together a presentation, and then I'm going to show you kind of a live view of how I shoot deep sky objects. So first of all, just kind of a definition of astrophotography. Astrophotography is all about taking pictures of deep sky objects. And the pictures that you take are long exposure photographs. So if you think about just taking a snapshot of something outside, the amount of time the shutter is open is very, very short because the sensor of the camera collects light from the object you're shooting, and that's how it represents an image. Astrophotography or deep sky objects are extremely dim, and so you need to take long exposures, meaning the shutter of the camera stays open for an extended period of time, a minute, 2 minutes, 5 minutes, sometimes 20 or more minutes. And you need to take a lot of them. So a digital photo is just a file of data, and you need to collect as much data as possible. It's really about capturing signal. What you're after is a high signal to noise ratio. And the more data you capture, every time you capture data, you're capturing signal data from the sky. And in that data is noise from the sky, like light pollution. There's also noise from the imaging equipment that you're using. So the objective is to maximize the signal, reduce the noise, and that's accomplished by capturing more and more data. Okay, so the equipment that we use. So here's a diagram of my equipment, and kind of the two key components are the telescope up here at the top and the equatorial mount, the Atlas EQG, down here on the bottom left. If I were to just use the telescope to observe the stars, planets, moon, I would only be using the telescope and the mount. I'd have a controller for the mount. Actually, that's what this picture is here. And I'd put eyepieces into the telescope, and visually you could look at objects in the night sky. But for astrophotography, you need a lot more equipment. Namely, you need an imaging camera, and for that I use a Nikon D5300. You also need a computer because all of this stuff is run by software. I'll talk about the software in a minute. There is a mount controller. This is a Nintendo gamepad that I use to control the mount. There's a component called a guide camera. This is a smaller camera that sits up on top of the telescope that locks onto a star. Usually it's a star near the object that you're shooting. And the software that runs that camera tracks that star, and any movement that occurs is corrected by sending pulses to the mount. Now this mount is completely computerized, completely motorized. It will automatically track the night sky, but to get the level of accuracy you need for astrophotography, you need to do some additional tracking, and that's what the guide camera is for. I also said this is an equatorial mount. If you look at the angle that this is pointing, it is parallel to the Earth's pole. And that's because in order for this to track the night sky, it needs to move in accordance with the Earth. So if you look at the night sky over a period of time, it looks like the stars are rising in the east and setting in the west. So it looks like the stars are moving. That's an apparent motion. Actually, the Earth is moving. And so your mount needs to copy that movement in order to track the objects. So we rely very heavily on aligning to the celestial pole. And the way you do that is do a polar alignment, and I have a special camera called the Pole Master that attaches to the mount here. You aim it at the North Celestial Pole, namely you aim it at the star Polaris, or the North Star, which is very close to the North Celestial Pole. And with this camera and software, every time I set up, I need to do that alignment. And once it's accurately set, my tracking of the objects I'm shooting should be very good. So all of this stuff connects through a USB hub, and also connected to that USB hub is my imaging PC. All of this sits outside with the telescope equipment, and I connect wirelessly to it using Windows Remote Desktop, so that when all this is set up outside and it's shooting images of a particular object, I can be inside on my other computer watching what's going on, managing it, and basically directing the telescope what to do. So this is an actual picture of my telescope with everything mounted. Here's the equatorial mount with its counterweights. All of this, by the way, is pretty heavy equipment. The tripod down here is about 20 pounds. The mount itself, which is this, is about 35 pounds. Each of these weights is 11 pounds. And the telescope equipment up at the top is probably 15 pounds. So it's a pretty heavy setup, and that's what makes setting up and tearing down so time consuming. You need to set this stuff up and align it every time you want to go shoot the night sky. The alternative is build an observatory and keep everything permanently mounted out there. Okay, so this is the telescope, obviously. Here's the polar alignment camera that's mounted to the equatorial mount, pointing presumably at the North Star. This is the mount itself. May be tough to see here, but here's my Nikon camera attached into the focuser of the telescope. Here is the guide scope that rides on top of the camera, and the little guide camera that attaches to that. In case you're interested, this is a refractor telescope, meaning that there's an objective lens at this end, and the imaging is done through the length of the telescope. It's 120 meters across. That's about 4 3/4 inches for the objective lens, and the focal length of the telescope is 900 millimeters. Okay, so that's the equipment. So let's talk about the actual capture process. So as I said, I don't leave my telescope out every night. Sometimes I do. I have a cover for it. If I know that the weather's going to be nice for a couple days, I'll leave it set up overnight, over a couple nights. That way I don't have to redo the polar alignment every time. If I leave it set up, that alignment doesn't need to be done every time. So when I do set up from scratch, I need to take everything outside. I set up the tripod and I level it. I add the telescope, the guide scope, the camera, connect all the cables, connect up the computer. So basically get everything all connected up. I do use AC power, so I run an extension cord out there. The AC power is to run the mount, the camera, the USB hub. So there's a couple things I need AC power for. If I were to do this out in the field with no power, everything would need to be run off a large 12-volt battery, or a couple of them. And if I'm doing a particularly long imaging session, I may need 2 car batteries to power them out, and everything I need to power for a night's worth of imaging. So once all that's set up, you need to balance the telescope. Balance is important to the tracking of the mount. If it's out of balance, the motors in the mount tend to stress a little bit more, so balancing the telescope is key. Once it's set up and balanced, I can then do a polar alignment. So I go to my laptop, I fire up the software for the PoleMaster software, and then I run through the polar alignment step, um, which the PoleMaster, pretty expensive piece of equipment, but it turns the polar alignment procedure from what could be a 15, 30, 40-minute task into a 5-minute task. And really, the accuracy of your polar alignment is really going to dictate um, the clarity and of your photos and the tracking that is required to take long exposures. Okay, once the polar alignment is done, now we need to focus the telescope, and that's usually moving the telescope to a bright star. And then again, everything at this point, well, I shouldn't say that. So to do the focus, I move the telescope to a bright star. Then I use a tool called a Bahtinov mask, which is just a mask with a certain pattern that you put over the end of the telescope, and it creates a diffraction image of the star, and you can use that diffraction image to get focus. Basically, you get the diffraction image into a particular configuration by moving the focus in and out, and once you hit the right configuration, you know that you are dead on focused to that star. And once you focus to one star, you should be focused for anything else that you want to shoot in the night sky. So once I'm focused, then I can start guiding. The telescope will automatically track, but the guiding is the thing that locks on to a particular guide star and can send corrections to the mount in case the tracking is off a little bit. Okay, as far as the software, so in order to direct the mount, I use planetarium software called Carte du Ciel. It helps me navigate around the night sky. It connects to the telescope, so when I'm looking at the planetarium, it'll tell me where the telescope is, and when I want to go to another object, I click on that object and I say go to it, and it sends a signal to the mount to go to that object. And I'll show you all that. There's plate solving software, guiding software, and then probably the most important is the imaging software. I'll jump down to the imaging software. So the imaging software is called Backyard Nikon, software that's built for my camera, and we use that to set up the imaging session. The imaging session is really telling the camera how many exposures to take, how long to take, what ISO setting to use. And then once you plug all that in, you hit go, and then the telescope is off and running, shooting images of the object. Now the images that it shoots through the telescope with the lens cap off, meaning it's seeing the night sky, those are called light frames. And those are basically just images that you're capturing of the light representing the deep sky object. There's other types of frames that you need to shoot. It's not just shooting pictures of an object. There's a whole process, kind of a post-capture process that needs to be done in order to get the type of photographs that we're after. So once you're done shooting light frames, there is a process or a type of frame called dark frames. And that's simply putting the lens cap on the end of the telescope and shooting the same imaging session, so the same number of exposures, the same exposure time, and the same ISO with the lens cap on. And what that does is it captures noise. Remember, we said that we are all about increasing the signal and reducing the noise so that we have a high signal to noise ratio. So in those light frames is most of your signal. There's some noise in there as well, but in the dark frames, you're capturing just noise. And the noise that you capture with the dark frames are noise on the camera sensor. So hot pixels, cold pixels. Remember, you're keeping the shutter open for 2 minutes, 3 minutes, 5 minutes, and that entire time the sensor is absorbing photons through the telescope. So that sensor is staying on for a large amount of time, and it's heating up. Just a regular snapshot of a vista or something, that lens, or sorry, that shutter is open for a split second, and the sensor captures photons in that split second, and then it shuts off. With astrophotography, that sensor is collecting photons for a long period of time. So over time, pixels on the sensor can go hot, can go cold. So there's all of those things end up in your light frames, and by capturing them in the dark frames, we can later subtract them out using post-processing software. So you basically run all of that, and that could be, I could say I want to take a picture of this nebula. I'm going to take 3-minute exposures, and I want to shoot it for the next 2 hours. And once I do that, I would then go outside, put the lens cap on, and run that exact same session with the lens cap on to capture the dark frames. So there's other frames. These are all called calibration frames that need to get created. There's flat frames and bias frames. Those I could typically do the next day because they're not dependent on things like temperature and duration of the exposure. But I'll talk about those in a second. Okay, the light frames. So light frames are long exposure images of the object that you're trying to capture. Light frames capture image signal, and it also captures noise. So if we take a look at a single light frame, if I were shooting the Andromeda Galaxy, and these frames, by the way, all went into that first image that you saw when I started this video, the image of the Andromeda Galaxy. This is what a single frame looks like of the Andromeda Galaxy. It looks almost nothing like the final image that we're going to get when we capture all the frames and process them together. So light frames are long exposures. It's got both signal and noise, and the idea is to capture a lot of them. So just repeat the same, using the same parameters of the camera, and just shoot over and over and over again. So by capturing more data, you're capturing more signal. You're also capturing more noise, but the noise is going to be subtracted out to the extent we can in a later step. So the dark frames are exactly the same as light frames, except you put the telescope lens cap on. You cover it up so it's really just shooting in the dark. And this is what captures hot and cold pixel noise on the camera sensor. And here's a representation of that. If you were to cover the lens of the telescope and shoot a 3-minute exposure, it could look something like this. And these are pixels that are firing. They're overexposed. Every camera has these. Every camera has a lot of these. You typically don't see them in a very short exposure photograph because the sensor is only firing for a split second. But they do become evident when you're doing long exposures like you need for astrophotography. So those are the dark frames. And those are both shot, the same night. The light frames and dark frames are shot the same time at night. And then, again, you shoot a lot of dark frames to capture more data on that noise to allow you to subtract it out. Now, the flat frames, these are kind of the interesting ones. These are short exposure images of an evenly illuminated background. So basically, an evenly illuminated background is kind of this screen, and in fact, a lot of people use a laptop screen of just kind of blank white or gray to shoot their flat frames. It captures the curvature of your objects, also known as vignetting. If you're a photographer, you know what vignetting is. I'll kind of show you that. But it captures the curvature of the objects, of the optics, and it also captures dust and dirt or anything else that might be in the imaging train. And the imaging train is basically everything between the sensor on the camera to the objective lens of the telescope. And so you have the sensor itself. You may have filters in the path. You have the objective lens, and then ultimately you're shooting the object in the night sky. So a flat frame, kind of a stretched version of what a flat frame looks like, but this is the vignetting that I'm talking about. It's kind of that circular ring that you end up seeing that represents the curvature of the optics. And you can't really see it here. I guess this might be considered one. This is kind of a dust bunny that's either on the filter I use, it could be on the objective lens, it could be on the camera sensor itself, but that gets captured. So everything you see here, and if you think back to the dark frame and all the hot pixels, all of that data in those frames is included in the light frames. It's all noise. And so by capturing them as separate frames, they can be subtracted out of the light frames. So all the noise that was captured in the light frames will ultimately get pulled out so that you can increase the signal of your light frames and have a good image. So again, with flat frames, you're going to take a lot of them, accumulate as much of that data as possible, and similar to all the other type of frames we do. The last set of frames are bias frames, and these are short exposure images with the lens, the objective lens covered. And what bias frames capture is camera read noise. Now, when a sensor absorbs photons of a photograph, once the shutter closes, that data is read off the camera sensor. And there's noise that results from that. It's not a lot of noise, but there's noise nonetheless. And you can kind of see this sort of grainy, this is a representation of a bias frame. And this is the noise that gets introduced when the pixels of the sensor unload their data into the camera buffer. And once again, like all the other frames, you capture a whole bunch of those. Okay, so doing astrophotography is not just taking one picture of an object. It's taking lots and lots of pictures, different types of pictures. So it takes a long time to get the data you need to ultimately produce a nice picture of an object. Some people actually collect this data, do light frames over multiple nights. You can see some pictures out there of nebula or galaxies where the amount of data captured is measured in many hours. So I could have 6 hours of light frames for the Andromeda galaxy. That amount of data will produce a great deal of detail in the image, much more than the one that you saw at the beginning of this presentation. That was maybe an hour's worth of capture on the Andromeda galaxy. So again, it's always signal to noise. You want that as high as possible. Maximize your signal, reduce your noise. Okay, once you have all of those, then the image processing takes place. This can be done, I usually do this the next day. Pre-processing is where you're stacking and aligning all those images. So you're combining the signal of the light frames and you're subtracting the noise from the dark, slats, and bias. I use software called Deep Sky Stacker, where you load up all of these frames and give it some parameters that you want to use and let it run. And it can churn away for, depending upon how much data, 30 minutes to an hour of processing on all of those images. Now, when I say stacking and aligning, stacking is the combining of the images. Aligning, the software can recognize, patterns of the stars. And so, for example, if the difference between one exposure and the other is that the telescope moved a little bit, the software can detect that and realign, the two photographs so that the stars overlap. And if you have lots of images, it does that with all the images. So you're stacking to combine signal, you're aligning to make sure all the images are aligned in the same way, and then ultimately the noise that you captured gets subtracted out. So after all that, you're left with a TIFF file, a TIFF formatted file, and then you pull that into some post-processing, some image processing software, like Photoshop is probably the one people recognize the most. You can use GIMP, and PixInsight is the one that I use. It is kind of a Photoshop specifically designed for astrophotography. And that's where you start to do things like stretch out the histogram of the image. I'm not going to get into what a histogram is, but that's how you pull out the data. Because if you think about it, an image of a night sky object, almost all of it is dark, right? It is a very faint signal that you're trying to pull out. So that's what you're after in the post-processing, to pull that signal out, to enhance the image, to make it more visible, to do noise reduction on it, to do all those things so that it looks like, you know, an amazing image of the night sky. And once all that's done, then I usually post them up to my Google Photos page, and anybody who's following my astrophotography album gets notified that I posted a new photo. Okay, so that's kind of the end of talking about the process. What I'm going to do now is go to Windows Remote Desktop, and I'm going to connect to my imaging laptop. And here it is. So I normally work on a Mac, but my imaging laptop is a Windows laptop. And that's because almost all the software that I need to do astrophotography is Windows-based. There are some Mac equivalents out there, but for the most part, the software for astrophotography is Windows first and Mac second. So really, if you focus in this middle area, this is the software that I use all the time. There's some other software that I use. So this is EQMod is the mount control. Polemaster is what I use to do the polar alignment. Carte du Ciel is my planetarium. Backyard Nikon is for image capture. Astro for Tortilla for plate solving. I haven't talked about that yet. And PhD2 for guiding. PixInsight and Deep Sky Stacker, these are the two tools I use when photo processing. I have a USB GPS that I can get coordinates. That helps by pushing your exact coordinates into the mount. It makes its tracking that much more accurate. Sequence Generator, that's kind of a new piece of software that I'm trying out. And Stellarium is a really graphical planetarium software. It's similar to Carte du Ciel, but much more graphical. And sometimes I use that as well. Okay, so on any given night, once my telescope is set up, it's balanced, it's leveled, it's polar aligned. Now what I need to do is connect to it. So I use ASCOM. ASCOM is a platform for astrophotography. EQ ASCOM is the tool I use to connect to my particular mount. So lots of software and hardware right to the ASCOM platform to be able to interface with it so that you can use your computer to control all of the elements of your astrophotography process. So I don't actually have my telescope set up, so I'm going to use the telescope simulator. So normally, if I had it set up, I would just use my setup for EQMod, but I'm going to use the simulator setup, and I'm going to connect to the mount. Okay, just normally it'll talk to me here. Let me shut that down again. We'll connect.
Rate 1.
Okay. So this is the software that controls the mount. It shows my position. I'm currently parked. Parked means that I am pointed at the North Celestial Pole. and it is not tracking. It's not moving at all. It's not following the night sky. I'm going to unpark it.
Unparked.
And now it's not parked, but it's also not tracking because it's pointed at the North Celestial Pole, which never moves. So nothing's going to move here until I actually find an object that I want to go to. These controls allow me to move the mount. So if I'm looking through the telescope and the object isn't centered, I can move these things to move the telescope. And then there's a whole bunch of parameters that are used. Certainly my location, so it knows my latitude and longitude, my elevation. All of that stuff is important for the accuracy of the mount. But really, once this is up, I can minimize that. I don't really need it. I just know that my mount is connected. The next thing I would do is run PoleMaster. And this isn't going to connect to anything, but normally I would say connect to my PoleMaster camera. It's not attached right now. And because it's pointing up at the North Star, I would see the night sky here. I would see Polaris. And then it would take me through a routine of aligning and adjusting my mount to make sure I'm polar aligned. And I'm not going to go through that because I don't have it connected up. But that usually only takes about 5 minutes, which is much, much faster than doing a manual polar align, which could take a half an hour or an hour. And I'd much rather save that time for imaging than for doing a polar alignment. Okay, so the telescope is on and running. I'm connected to it through EQ Mod. And now I'm going to start up my planetarium. And this is what I use to figure out what I'm going to look at, to move the telescope around. It's basically a sky chart of the night sky. And let me just pull that down. Okay, so this is actually showing the sky now. Here's the sun. I'm doing this during the daytime. But normally what I would do is I would align this north. Here is the North Pole, the North Celestial Pole, and I can zoom in on that. And so you can see that that's Polaris, that's the North Star, but the North Celestial Pole is a little bit over here. So Polaris, while we call it the North Star, is not exactly on the North Celestial Pole, and that's why we need to do an alignment. But Carte du Ciel also understands the ASCOM protocol, and so I'm going to tell it to connect to the mount. So I'm going to say select the simulator, say OK, and then I'm going to tell it to connect. And you'll notice over here I now have a bullseye over the North Celestial Pole, and that's telling me that the planetarium software is now connected to my telescope. Okay, so now I need to pick an object. So this is kind of zoomed out here. I know there's a galaxy over here. If I click on this, this is M76. That's a planetary nebula. So I can get kind of some information about it. But let's say that's the object that I want to image tonight. So all I do is tell the telescope to slew to that object, and you'll see it's now moving the telescope over to the object. So it's doing this automatically. And again, I'm usually inside when this is happening, so I'm just assuming the telescope is moving correctly. But now I have to confirm that I found it. And that's where the imaging capture software comes in. And that is Backyard Nikon. So I'm going to start Backyard Nikon. And while I do that, I'm actually going to connect up my camera so that you can see what it's doing. Okay, So what I'm going to do now is tell it to connect, and I'm connected. So it says up here my D5300 is now connected. And over here is where I have my session information. A lot of times what I do is take a single exposure of where I'm just pointed. So I was supposed to have gone to M76. And if I take usually I'll just crank this up a little bit, so maybe 4 or 5 seconds. Take a preview image. So the camera shutter just opened. It's taken a 5-second image. Now I have the lens cap on the telescope, so we're just going to get a black frame. But if I was pointing at the sky, you would actually see some stars in here. Now, the accuracy of pointing to that object just on the first try is not that high. And in fact, the object I'm shooting may be over here, it may be up here, and I need to center it. So, I could kind of use my little mount control here and move these controls to move the mount, and then take another preview and see if it moved the right way. One thing to note is north, south, east, and west is not up, down, left, and right. It depends on how you're pointing in the night sky. So if I move north, if I click this a couple times and take another picture, the image could have moved this way. So north, south, east, and west is not terrestrial north, south, east, and west. So instead of trial and error in trying to get my object in the center, we use something called plate solving, and that is the program I use is Astro Tortilla. Kind of a cool name. I don't know why they call it that, but it works, and it's a real big time saver. It's also ASCOM compliant, so I'm going to tell it to connect to, in this case, the simulator. Normally I would be using that EQ6 setting, but I'm not connected now. And so now it's connected. So it's also tracking because I went to a target. So it knows the target that I'm after is over here, and this is its right ascension and declination coordinates. But this is telling me where it's actually pointed. And it's not exactly, it's pretty close, but those things don't line up. So that means that the object is not going to be centered, and I need to center it. So what happens now is I'm going to click these actions. And what this will do is when I say capture and solve, it will take a 10-second exposure using Backyard Nikon. I can watch it all happen. And when it gets that picture, it's going to plate solve. And the process of plate solving is taking that image and comparing it to gigabytes worth of star charts that I have installed on my laptop until it does a pattern match to find the exact location it needs to be. Once it does that, it now looks at the delta between where it should be, which is the target, and where it currently is, and it sends a signal to the mount to center the object into the frame of the camera. Then it takes another picture to show me that happens. So one way I can show you how it works is I'm going to disconnect from the camera. I'm going to switch this to File, Open Dialog Box, and Tools, and I'm going to say Go to Image, and I'm going to pick this image. So this is an image I shot the other night of the Jellyfish Nebula. It is a single light frame. I guess I have to have the telescope connected. So let me do that. Somehow lost AstroTurf. There it is. Okay, so I'm going to say, all right, go to image, select that image, and so now you kind of watch down here. It's reading the input file. It's examining it. It's then going to downsample that image, and that's going to tell us how many stars. So it found 964 stars in the image, and now it tries to pattern match. It's going through all the indexes, parses the results, and it's slewing. So it's actually sending a signal to the mount. And if we were to go look over here, we would probably see, let me do this. Probably should have had this, I don't know where it went. Oh, did I disconnect it? No, it says it's connected. Oh, I think I know what happened. Because I plate solved on this image, which was the Jellyfish Nebula, I think it actually slewed the telescope to the Jellyfish Nebula. Let me see. That should be in Gemini, which I don't think is even above the horizon. So not sure where the telescope went, but I think you get the idea that all this is being used for is to center the object. And if you want to see what that that picture looks like that we used, I will open this up. So this was the image. Here actually you can see some nebulosity, but it used this picture. You can see why it found 964 stars. There were a lot in there, but it figured it out, found out where it was. And if this were M76 that I thought I was going to, that object would be dead center in the center of the image. Okay, so once I've done the plate solving and I know my object is centered, I really don't need these anymore. Now I'm going to go to Backyard Nikon, and I'm going to say, all right, I want 50 images. I want to shoot it at ISO 1200. ISO is the sensitivity of the camera. If you go too high, you're adding noise, but you'll get noise due to light pollution and things like that, where it's going to look overexposed. And then usually what I do is, I'm going to take pictures in the 2-minute range. Sometimes I'll go 180 seconds, 3-minute range. Once I get my guiding, much better, I'm still learning that, I could go up to, 3-minute range. And then I click Start Capture. I do give it some information like the target. So I'm going to shoot M76. And this is used to create the files, the file names. And then I say Start Capture, and it'll tell me when it's going to finish. So this is going to be a long time if I'm doing 50 of them. When it's done, I need to go back outside, put the lens cap on, change this to a dark frame, and then hit Start Capture again. So if this took, 2 hours to shoot the light frames, I run outside, I put the lens cap on, and then I shoot another 2 hours just capturing dark frames. So on any given night, however many hours I shoot of light frames, I have to do the equivalent in dark frames, so that doubles the amount of time that the equipment is out there and set up. Okay, I think that is all I wanted to talk about. I could show, well, let me just show you the kind of just what it looks like from a file perspective. If I go into Backyard Nikon, so just the other night I was out I started by shooting the M44, which is the Beehive cluster. I ended up shooting the Jellyfish Nebula. And here's all the data. So as I scroll through here, there's the bias, the darks, the flats, the lights. I've got lots of them. I think I had 60 light frames. Kind of screwed up on the darks. I didn't get as many as those. I got 20 or 30 flat frames and all the bias frames. And then, once I'm done and I have all that data captured, this is Deep Sky Stacker. This is where I say, okay, this is the software that's going to stack and align. So I'm going to tell it, okay, here's all my light frames, going to pick those. Then I do the dark frames, the flat frames, and the bias frames. Load all that stuff up, hit register, and off it runs. It'll run for a good long time and ultimately create a TIFF file, which I think we saw here. Yep, here's the TIFF file. And if I open this up, I want to open with PixInsight. And this will take a second, but even at this point, it's not going to look like the final image. In fact, for the Andromeda Galaxy, like we saw before, the final image after stacking isn't going to look much different than a single image. All that data needs to be processed and stressed and have noise reduction. Okay, so the picture that I took was this is actually the Jellyfish Nebula. This is what it looks like after it's been stacked. It looks like a bunch of stars. You can't really see anything. And that's because we haven't stretched it out. We haven't taken the image from being a linear image to a non-linear image. The quickest way to do that is to use this screen transfer function. Here it is. And what this does is it can do a quick stretch. So if you look at this image, I'm going to do an auto stretch of the histogram. And it's lagging a little bit, and there you go. So we stretched it out. We basically took the area of the histogram where the image was, stretched that out so that we could see more of it. And now this is really my starting point for the image post-processing. So you can see there's a lot of nebulosity here, but there's also kind of some gray area in the middle. You can see the edges are darker. This one actually did not have the flat frames applied. So if you remember that vignetting and the bright spot in the middle and the darkness on the edges, this is a good example of an image that did not have the flat frame noise subtracted from it. I think I've fixed the problems we were having. So this was the image of the Jellyfish Nebula. I put a stretch on it. And now I'll just show you one step that I always do, which is the automatic background extractor. The thing I forgot to do last time is tell it I want to, oops, the correction I want is subtraction. And I just drag this onto the image. And as I said before, it's going to basically turn that into two layers, the kind of star and nebula layer, and then the background noise that's introduced by the objective lens and dirt and dust and things like that. Okay, so this kind of looks like the original one we started with before I stretched it, but this is the background, and if I stretch the background, you'll see there's all that kind of gradient and vignetting. And so by doing this background extractor, it pulls all that stuff out. So here was the original image. You can see that kind of haziness in the center, darker on the edges. And then this is the background that we pulled out. So I'm going to get rid of that. We don't need it. And then this is the image with that background pulled out. So I'm going to stretch that. If I can get my mouse to work. There we go. So now you're starting to see much more of the nebulosity come out of the picture. There's much more processing that needs to be done. There's noise reduction, there's gradient removals, things like that. This is really just kind of the initial step. And then I'll end with, after I use PixInsight, I still use Photoshop to do kind of some final touch-up, and I'll bring that up. And this is Photoshop. This is that same image, kind of at the final stage, and this is that jellyfish nebula. So that does it. I will, if you have any questions, you can post them in the comments. Otherwise, thanks for watching. Bye-bye.